let's go to this problem. Yeah. So Bessie, there's n months, each with A1 to AN days, respectively. And there's also weeks where each week is L days, with L being a positive integer. Yeah, so there's some conditions on the number of weeks that we can have. So each month is at least 4 weeks long. So basically each AI is at least 4 times L. And then yeah, for the correct L, there are at most 3 distinct values of AI mod L. Yeah. Um, yeah. Okay. Yeah. So and it's asking you to find the sum of all the possible values of L. Um, yeah. So I guess in this case, these are the months. They're around 30. Yeah. And then you can show that these are possible values of L, because for L equals 7, each month is 0, 2, or 3 mod L. Yeah. And then the constraints for here is AI is at most 4 times 10 to the 9. And then the subtask is like uh, AI is at most 10 to the 6th. Yeah. Um, yeah, and then also n is at most 10 to the 4th. Yeah. Uh, yeah, so let's see what's true, like let's see what conditions might hold if a particular L works, right? Um, so let's see what conditions are true for a valid L. Okay. So we know that there has to be at most 3 distinct values mod L, right? Um, so basically, like one thing that we know, if 2 things are equivalent mod L, basically, um, like if AI and yeah, so basically there's 3 distinct values mod L. Let's say they're like C1, C2, C3. And then if AI is equal to C1 and then AJ is equal to C1 mod L, that basically gives us that L divides AI minus AJ, right? So basically, uh, yeah, if any 2 things are the same mod L, then that means L divides AI minus AJ. So just consider this some kind of graph, right? Yeah. So consider a graph. Of course, given the constraints, yeah, so we can't like construct this graph for every L. But let's say that there's a graph where there's an edge from U to V if L divides their difference. So edge from U to V if L divides AU minus AV, right? So what can we observe about this graph? So basically, uh, for everything that's if these are your distinct values, for example, for everything that's equivalent to C1 mod L, they're going to form a connected component, right? Because L can yeah, L can divide the difference if they have the same residue mod L, right? So if we construct this kind of graph where there's an edge from U to V, if L divides the difference of the elements, then that means there's going to be at most 3 connected components. Right? Um, yeah. Oh yeah, one more thing. Yeah, just assume the values of AI are distinct. if there's duplicates, it doesn't matter. Or we can just reduce it so it's distinct. Yeah. So if there's an edge from U to V, if L divides AU minus AV, since there's at most 3 distinct values mod L, then there's at most 3 connected components. So there's something called a pigeonhole principle. If you have you might have heard of this. If you have like k minus 1 pigeons in k holes, then there exists a hole with more than 1 pigeon. So if you just consider the first 4 elements, A1, A2, A3, A4, and you assume they're distinct, then this will be in some component, C1, C2. So there's up to 3 components, right? C3 and C4. And there exists 2 elements that are in the same component. So, right? There exists 2 elements that are in the same component, right? So for any L, if you just consider the first 4 elements, there exists 2 elements that are in the same component. So basically for any L, like there exists 2 elements among the first 4 that it divides. So for any L, L divides AI minus AJ for 1 less than or equal to I less than J less than or equal to 4, right? So we can use this as a way to consider our candidates for L. So basically candidates for L is like divisors of AI minus AJ, where 1 less than or equal to I less than J less than or equal to 4. So basically, number of ways to pick this IJ pairs is like 4 choose 2. So 6 numbers. So basically there's six ways to pair them, and L has to be a divisor of one of these pairs. And we have from the constraints that it's up to 4 times 10 to the 9. So basically we can just iterate over the divisors. So basically number of candidates for L is like most like square root 4 times 10 to the 9 yeah times 6. Yeah, I think you can show something stronger, but the idea is that there's not that many candidates for L, so then you can just do brute force to check if L is valid. Yeah, so to check if L is valid, yeah. Yeah, so to check if L is valid, you can find the remainder of L modulo all the AIs from A1 to AN. And if you get at most 3 distinct values, then that's a valid L. Yeah. I think, yeah, you can probably show something stronger, like this to the power of 1/3, but it's just a weak bound. But yeah, you can, yeah, so the number of candidates for L is small. I'll just summarize the idea again. Since there's 3 distinct values, mod L, you can construct a graph, or just like not explicitly construct it, but just consider the graph where there's an edge from U to V if L divides AU minus AV. And if you consider the first 4 elements, then by the pigeonhole principle, you know that 2 of them must lie in the same component. So that means L must divide AI minus AJ for some IJ. So, and since we only have 4 elements, then there's 6 candidates for AI minus AJ, and you just find the divisors of all these AI minus AJs. And this gives you a small number of candidates for L, and you can brute force to check if L is valid and compute the sum from there. Yeah. Any questions? Yeah, so that's the solution for problem 3. Yeah, so yeah, probably like problem 2 is more of a standard problem, and problem 3, yeah, you need to make some observations. Yeah, it's a bit tricky, but um, yeah, but coming up with it is a bit tricky. And then problem 1 is yeah, yeah, problem 1 was probably the trickiest one. Yeah, it'll be on YouTube. Yeah. Yeah, I guess for problem 1, uh, like this task for input 3 is doable. Um, yeah, like you can get free points with brute force. Um, yeah, yeah. Yeah, that's it for my solutions for the silver. But yeah, any questions?
Yeah, here, Arvin, yeah, here the summary page. Maybe you can use these slides to give a quick summary.
Yeah, so for competency, which I think was the most tricky problem, there were a lot of like greedy arguments that we made, like certain arguments about the structure of the intervals, like looking at the optimal solution, and then certain arguments about what elements we need to place to give the lexicographically smallest solution. Yeah, so this was a greedy problem. And then potion farming was maybe more of a standard problem, but it is a tree problem. And you have to make use some greedy arguments to argue that you want to match the lower potions first. And then yeah, and then a way to implement this efficiently was with using recursion or DFS. Yeah, and then calendar was a number theory problem. And then yeah, and then also requires like some observation using pigeonhole principle. But yeah, um, yeah, about cutoff estimates, I'm not really sure, but I personally thought uh, problem 1 was definitely hard for a silver problem, and then problem 2 was probably standard, maybe on the easier end, and then problem 3, um, um, hard to say. Maybe the observation is like kind of clever, but I don't think it was like extremely hard for silver.
Thank you, Arvin. Do you see any